Protein synthesis is a three-step process, including initiation, elongation, and termination. In bacteria such as E. coli, initiation requires three small proteins called initiation factors, IF1, IF2, and IF3, as well as the first tRNA, the mRNA, and the small ribosomal subunit, also called the 30S subunit. IF3 readily binds to the small ribosomal subunit, and its presence blocks the large and small subunits from prematurely associating. IF3 facilitates the binding of the mRNA to the small subunit of the ribosome. The binding occurs just 4 to 8 bases upstream of the AUG start, where a consensus sequence called the Shine-Dalgarno sequence in the mRNA anneals near the end of the 16S ribosomal RNA in the small ribosomal subunit. IF1 binds to the small subunit at a location called the A site, where incoming tRNAs normally bind. The first tRNA, called N-formylmethionine tRNA, thus enters another site called the P site. Note that the initiator tRNA has been escorted to the P site by IF2, which is bound to GTP, a high-energy molecule similar to ATP. The anticodon of the tRNA is complementary to the AUG start codon. Once the initiator tRNA is in place, IF3 is released. With the loss of IF3, the 50S subunit can dock on the 30S subunit. The docking of the 50S subunit triggers the hydrolysis of GTP on IF2 and the subsequent release of the initiation factors. The ribosome is now ready for elongation. Elongation involves the repetition of three steps. First, an elongation factor called EFTU, associated with GTP, binds to free charged aminoacyl tRNAs. This complex enters the A or acceptor site. Correct selection of the tRNA complex depends mainly on codon-anticodon pairing. In this example, the anticodon CCC pairs with a GGG codon. The tRNA carries the amino acid glycine. In the second step, the ribosome's peptidyltransferase activity catalyzes the formation of a peptide bond between the new amino acid in the A site and the previous amino acid in the P site. Simultaneously, GTP is hydrolyzed and the resulting EFTU-GDP is expelled. The third step is called translocation. An elongation factor called EFG, associated with GTP, binds to the ribosome. The GTP is hydrolyzed, providing the energy to ratchet the 50S and 30S subunits ahead one codon. This maneuver opens up the A site and slides the uncharged tRNA into the last site, called the E or exit site. The next aminoacyl tRNA that enters the A site creates a conformational change in the ribosome that telegraphs through to the E site and ejects the uncharged tRNA. These elongation steps repeat along the mRNA. The ribosomes of E. coli can speed through these elongation steps, linking together 16 amino acids per second. Eventually, the ribosome arrives at the end of the coding region, marked by one of three stop codons. This stage of translation is called termination. No corresponding tRNAs exist for stop codons. Instead, a protein called a release factor, either RF1 or RF2, which has the general shape of a tRNA, mimics a tRNA and enters the A site. The release factor activates the peptidyltransferase function of the ribosome, which cuts the bond, tethering the completed peptide to tRNA in the P site. Another factor called RF3 then triggers RF1 or RF2 to depart the ribosome. Finally, another factor called ribosome recycling factor or RRF, along with EFG, binds at the A site, and the accompanying GTP hydrolysis undocks the two ribosomal subunits. IF3 then reassociates with the 30S subunit, preventing the 50S and 30S subunits from coming together again. The liberated ribosomal subunits are now free to diffuse through the cell, ready to bind yet another mRNA and begin the translation sequence anew.